Hello, this is Jeremy Comel and welcome to LipidMatch tutorial part 7. In this tutorial, we're going to discuss all-ion fragmentation. So in all-ion fragmentation, you have versus data-dependent fragmentation where you select one ion, fragment it, and measure those fragments. In all-ion fragmentation, you send all the ions to the collision cell, fragment all the ions simultaneously, and then detect those fragment ions. In this case, we lose the relationship between the fragment ion and the precursor ion because we're no longer selecting individual ions for fragmentation. So we don't know whether this ion came from this precursor or from that precursor. So another analogy is a Lego analogy. If you had data-dependent analysis, you might have one Lego piece that you take into multiple pieces, and from those pieces you can use a little manual to rebuild your starship. Then in all-ion fragmentation, you might have multiple Lego kits, and let's say your kid breaks them all into pieces in a giant pile. Now you have to reconstruct the original starship from all these pieces, and it becomes much more complicated. So we have to be able to reconstruct that relationship between the precursor ion and the fragment ions to reduce the chance of false positives. The way we do this in LipidMatch is by looking at the precursor ion profile, elution profile, and chromatographic time. And then we look at a fragment, let's say the neutral loss of the phosphotidylcholine head group. And if that came from the same precursor ion, it should follow the same elution profile. And then we look at another fragment needed for confirmation, and if you have all the fragments following the same elution profile as the precursor ion necessary for confirmation, then you can confirm the identity using LipidMatch. The way LipidMatch does this, we showed visual alignment here. It does a correlation between the ion intensities of the precursor ion and the fragment ion, and then it uses an adjusted correlation coefficient cutoff. For example, an R squared of 0.6, and anything below that cutoff is not considered a fragment that was confirmed. So let's go into how we can run all-ion fragmentation data using LipidMatch. First, we're going to start with the all-ion fragmentation .raw files from Thermo, and we are going to convert them into .ms1 and .ms2 file format using msconvert. So we open up msconvert and we first upload those files. And once those files are uploaded, then we can choose the same exact parameters as we did previously for data dependent in LipidMatch tutorial part 2. And so we can press start. Now the difference here is that not only are we going to save the .ms2 files for all-ion fragmentation, but in order to do that correlation between the precursors and the fragments, we're also going to save the full scan data, so ms1 level. So we'll do the same parameters. We'll go to peak picking, and now we're doing level 1 and 1. We're going to go to thresholds, absolute intensity, most intense, again, 0, 0, 0, 1. And then we're going to finally go to MS level and just MS level 1. And we're going to change the output format to MS1. Make sure that all of these parameters are the same, and then click Start. And once this is finished, then those data files should be saved in the same directory that you imported them from. And so we'll close msconvert. We'll look at our AIF data, and indeed you do have 2 files for each raw file, one ms1 and ms2. So let's put that in our input file folder. Now you see in our input file format folder, we're going to have the all-ion fragmentation data, and note that it has to end in either neg or pos, depending on the polarity. And for each raw file, you should have an MS1 and an MS2 file with exactly the same name. And this name somewhere in the file name should be all-ion fragmentation, AIF. Those 3 letters should be in your file, so it knows to pick those and treat them as AIF files. In addition, you see in this input file we have some data-dependent files, as we discussed generating in LipidMatch tutorial 2, as well as our feature tables, which we also discussed in tutorial 2. And so we can run LipidMatch and analyze both data-dependent and all-ion fragmentation simultaneously, and they'll append both of those identifications onto the feature tables. So now we run LipidMatch. So we'll go into our LipidMatch code, open it up, press Control A, and then select Run. Again, the pop-ups might appear behind the RStudio console, so you might minimize the RStudio console to find them. In this case, I have a new version of R to download. As long as you have 3.1.0 or above, it should be okay. So I'm going to click No, not install the new version. Now, in terms of input directory of MS2 and feature tables, this is the folder, the LipidMatch input folder, where we had all the data-dependent feature table and AIF.ms1 and .ms2 files. Press OK. Input directory of the libraries that came with LipidMatch. And then these are all the same parameters as we've discussed in LipidMatch tutorial 3 for data-dependent analysis. So I'm going to select the defaults and then find the columns that have the row ID, which in this case is 1, mass of charge 2, retention time 3, data start 3. Again, this is discussed in LipidMatch tutorial 3. Now, additional parameters will appear if you have all-ion fragmentation data. So for example, they're now asking for the minimum adjusted correlation coefficient, or R squared, value for all-ion fragment conformation. So we showed what this represents earlier in the PowerPoint presentation. So I'm going to go for a default of 0.6. That's saying the correlation between the precursor and the fragments, all of those necessary for conformation, are 0.6 or greater. Now, another parameter is the number of scans you need that match between the precursor data and the fragmentation data. And I would not go lower than 5 scans, because you'll need a number of scans to make sure and be confident that the elution profiles of the precursor and the fragment ions match up, and to reduce false positives. The more scans, the more positive you are. So we could go with 6 scans, for example. Then, of course, you have the minimum number of scans for data dependent, as we've discussed before. We'll use 1 for Orbitrap mass spectrometers, and press OK. And so now you can see again that the LipidMatch code is running, and when it's finished running, the stop will disappear for good. Now let's look at, it's important to note that the all-ion fragmentation code takes a long time to run depending on the amount of lipids you have in your data and the number of data files. So it could take over 6 hours in some cases. So we're going to look at some sample output that was previously generated. And you can see that there's both a data-dependent output folder and AIF, as well as the files containing all the appended information. If we look at neg ID'd, for example, it's going to have our feature table with the row ID, mass of charge, retention time, the sample groupings, the peak areas. And now it also has identifications. If we scroll down, we can see 2 underscore means that that identification was identified by all-ion fragmentation. So anything with a 2 underscore was identified by all-ion fragmentation. 1 underscore again is data dependent. 3 underscore is data dependent by class. Now, if we look into the AIF folder, we go into one of the polarities, and we go into additional files or confirmed lipids. You can see here's the information pertaining to all your confirmed lipids. So here we're looking at lysophosphatidylcholine, and we can see if we scroll to our right, a lot of different types of information, but I'm going to keep scrolling to the right until I get to adjusted R square, and this will give our parameter that says greater than 0.6. And here you can see for each lipid ion, so for example 14:0, the formate adduct, you can see the correlation coefficient scores, or R squared values, for the precursor in this case versus the neutral loss of the methyl group in the formate adduct, as well as the precursor versus the fatty acid fragment. And you can see that both of them are very highly correlated. In addition, if we scroll further to the right, we see the slopes of that correlation, which is indicative of the ratio of the intensity between the precursor and the fragment ion. So here again is our two correlations between the neutral loss of the methyl group and the formate adduct, and that slope, and the precursor and the fatty acid ion. And so you can see in this case, the precursor, this is the fatty acid ion, much higher slope, 0.4 for example versus 0.04 in most cases, which means that the fatty acid ion is much more intense in relation to the neutral loss of the methyl and the formate group. So you can look at all that information for all your ions confirmed, and that will conclude the tutorial on all-ion fragmentation using LipidMatch. Thank you.